Okay, now this particular session is on reverberation time and particularly on Earring's formula for predicting the reverberation time in the space. In this particular formula here, T is obviously the time, V is the volume of the space, S represents the surface area of the space, and this particular term here, this alpha bar, is basically the mean absorption coefficient of the room. This particular log function key here is actually natural log, so it's not logs to the base 10. Natural logs are actually logs to the base E. So when you've got calculations that involve Earring's formula, remember that we're dealing with logs to the base E and not logs to the base 10. Okay, it's a common error that we see in some examinations. So in this particular problem, okay, what we're going to do is we are going to rearrange this formula again, but we're going to rearrange it this time for alpha. So that's what we're going to aim for. Okay, looks a little bit hideous to get to there. It'll take a few stages. So I'm going to try to split this board into two, and hopefully we'll get there in the space that we've got. So the first thing to recognise is that the log term in this case is actually at the bottom. So we need to take this log term to the top. So what we'll do, I'll just put a line down the bottom here. Start off on this side. We'll keep the 0.16v as it is. So we've not moved that. The t that we've got here will stay as it is. But the log that we need to do here, we're going to take this term entirely to the top. So we end up with log 1 minus alpha. Now I think we can try to push this out a little bit, because what we're trying to do now is that we'll take the t at the same time, we'll take the t across to the side. Obviously all we need to do is to switch the t and the log term together. So this t comes down here, okay, and the minus s remains where it is. Now we can put the minus in front of that term, okay. Doesn't matter if it sits down here or if it sits up there. So we'll put the minus in front of the whole term. So we've got to this point here. The next thing we need to do is to get rid of the log term, because at the moment what we've got is that we've got the alpha bar tied in with a log. So we need to anti-log both sides again. Now this time though, remember that we are anti-logging a natural log. And we're anti-logging a natural log, we're actually raising it to the power e. So we're looking at e to the power x. Okay, so what we're doing is converting it into that form. If we anti-log this term here, very much similar to log to the base 10, the ln simply disappears. So we end up with 1 minus alpha bar. In this side here, this all has to go into this function here. So this becomes e to the minus 0.16v divided by s times t. Okay, so we've got to a situation that we've got rid of the log, we've got this term tied up very nicely. We can see that this is a negative term here, so we have to make it positive. So we can take it across the other side, it then becomes a positive term. At the same time, we can leave the 1 where it is, okay? We can take this term, which is positive, over here, and that becomes a negative. So that becomes e to the minus 0.16v st. So that's how you would actually rearrange that. Okay, so in the particular room you can try some numbers in here. Okay, so what we can do is simply we can give you the volume of the space. So if I give you some dimensions to try out, imagine we've got a 6 by 3 by 2 meter high room. This works out at 36 meter cubed. Okay, imagine that we're told that the reverberation time of that space is 2 seconds, so it's a highly reverberant space, so it's likely to have a very small absorption coefficient. If we work out the surface areas from these dimensions that we're given here, okay, so they're basically a ceiling of 6 by 3, we've also got a floor by 6 by 3, we've also got a 3 by 2 wall, we've got 2 of them, and we've got a 6 by 2 wall, we've actually got 2 of them as well. I think if you do the maths I think it comes out to 72 meters squared. So what we can do is to put those parameters in here. Okay, so we can put a value in for S, which is 72, put a value in for T, which is 2, and the volume, which is 36. If we do all that, we end up with e to the minus of 0.04. Okay, so that, if you do the maths, and if our maths is correct, okay, this works out, remember we're working out the alpha here, I believe that this works actually out uncannily to a figure of 0.04. Okay, so what we've tried to do there is sort of unpick this particular formula, okay, and work out a mean absorption coefficient for a space. Okay, but the key point here is don't fall down the trap of assuming that's log to the base 10. It is actually log to the base c. Okay, that concludes this tutorial.